Okay, good morning. I'm Peter Michelson. I'm the chair of the physics department here at Stanford University. And on behalf of the university, I'd like to welcome you to the second annual Breakthrough Prize in Fundamental Physics Symposium. And I think we have an exciting day, a number of wonderful talks ahead. And I'd also, before we get started, just like to acknowledge the founders of the Breakthrough Prize, in particular Yuri Milner, who will be with us. Yuri, are you here? No, he'll be with us this afternoon for the panel discussion. But before we get started, I'd just like to say a little bit about, so why do we do fundamental physics, and what is fundamental physics research? And I'm just reminded of something Albert Einstein said, which probably you've all heard, that if we knew what it was we were doing, it would not be called research, would it? And so I think that applies to much of what we do. So with that, we'll hear about what a number of people are doing, and we have 3 sessions: cosmology, quantum information, and quantum gravity and particle physics. So Yasunori, would you chair the first session? Thanks.
Thank you. Thank you. Hi, welcome again to the Breakthrough Prize Fundamental Physics Symposium. In this morning session, we will hear 3 talks from our distinguished speakers. I'm the chair of the session, Yasunori Nomura from Berkeley. Our first speaker is Andrei Linde, Harold Tripp Friis Professor at Stanford University, and he's a recipient of 2012 Breakthrough Prize. Today, we hear from him about inflation-density vacuum in supergravity and string theory.
Okay, so I guess I should be quick. Now, I should say that what I'm going to talk about is about inflation in supergravity and string theory, something about uplifting. This will be, well, very incomplete in the sense of even covering what is done here at Stanford University, in particular some of the best works on inflation and supergravity, inflation and string theory are done by Eva Silverstein. Well, she talked here last year. I will be covering something else, which was made in collaboration with a very large group of people, in particular, especially with Renata Kalish. So if any questions about supergravity, you know whom to ask. Now, concerning cosmology in general, during the last, well, maybe 20 years, 30 years, we had 2 major cosmological surprises. One is that apparently there was a stage of very fast, exponentially rapid expansion in the very early universe, which is called inflation. And another one, and that's the subject of this year, well, prize winners, is accelerated expansion of the universe now, dark energy. And here is the simplest toy model, which can explain and describe both of these regimes. So first of all, you have some part of your energy which may look as simple as a harmonic oscillator, and here are some other terms which I am not writing here explicitly. And then another thing is there's tiny, tiny addition. And this tiny addition is only 10 to the minus 120 in string unit, in Planck units. So you could say, or ignore it. And therefore, for all purposes of inflation, you can indeed safely ignore it. But it describes the present stage of acceleration, which is essentially inflation now. And we will find out that it is, well, not always easy to unify these 2 small pieces. And that is going to be about uplifting and how we can do it. So our goal, finally, is to find inflationary models together with stable de Sitter minimum with this tiny, tiny vacuum energy 10 to the minus 120. So far, the best hope of finding it is related to string theory landscape, but what we are trying to do is to find effective description of this thing in terms of supergravity, which is a stage below, but it allows us to develop some interesting intuition, as I hope we will see. So first of all, the simplest models of inflation and supergravity. For many years, we have lots of problems of finding any reasonable model of inflation and supergravity, and suddenly we have lots of them. These are based on some previous works by some group of Japanese people, especially by Yanagida, but we have extended them. So you can take Kähler potential of this very generic form. You can have superpotential, which is some function, some field S, and that is a general real holomorphic function of this field phi, which will play the role of the inflaton field. In this case, it's a real part of this field which will play the role of the inflaton field. And then under certain conditions for stability of imaginary part of this field and the field S, the potential for the inflaton field will be given just by the square of this function. So you take the simplest function, for example, linear function. So it would be S multiplied by phi, and then you get quadratic potential. You get the simplest model of chaotic inflation there. So it's amazingly simple, but also because right now, after this works, we have a functional freedom of choosing this potential. Then we can have inflation in supergravity describing whatever set of experimental data giving you an S and R, these two parameters, which are the main goal of finding at, say, at Planck, using Planck satellite. So we have two major issues with this set of models. This one is not major, but it's technical inconvenience. If we want to stabilize imaginary part of the field phi, usually it's just pretty easy. It's almost automatically in most of the theories. If we want to stabilize this field S, which is Galstina, then sometimes, and actually quite often, we need to add additional terms to the simplest Kähler potentials. So having a freedom of having a generic one, this is not a problem, but nevertheless, it's unpleasant that at some crucial moment you start with something which need to be a little bit extended. The second thing is that usually a very good approximation to start with, saying there is a low energy phenomenology, what is this 10 to the minus 120, but let's start with something decent. Something decent is like, if we start here with this F, just phi. So phi goes from plus infinity to minus infinity. At some point, it crosses 0. You take a square root. You get a parabola which has vacuum energy equals 0 at phi equals 0. So that's very nice. If you have a simplest function, generic, and you get a minimum exactly in Minkowski, and that's a very good initial data because we have like difference 10 to the minus 120. Now, and also in this minimum, supersymmetry will be unbroken, and that is for, well, you may just check it. Well, so now it could seem very easy to just modify a little bit Kähler potential and superpotential in this theory, and we'll adjust it a little bit and get 10 to the minus 120. So apparently this is not the case. There is a no-go theorem of doing it. If you are in Minkowski space with, in supergravity with UZ unbroken, then by small modifications of Kähler and superpotential, you cannot actually uplift it. You can only downshift it if you want. And that's not what we want to do. So usually this is a problem. Also, here UZ is unbroken, and we need it to be a little bit broken. So of course, you can do what people usually do. You just add other fields. Now, once you add other fields, your theory right now, it's already a theory of 4 fields, okay, because each of them is complex. Now you add another one, and you have a problem to solve. And here, everything was simple, because the only moving part was the inflaton field. All the other 3 degrees of freedom are just crossed out. If you modify it just a little bit, then everything starts moving. So now, one possibility which we studied during this year is something which was brought to us long time ago, even before, well, the standard supersymmetry formulation was, well, developed. So it was Volkov-Akulov formulation. And in Volkov-Akulov formulation, there is, something special about some of the fields. You can just ignore, remove scalar fields from the description, replacing it by some, well, binary combination of fermions. So now this was done in global supersymmetry, and what was done this year in a set of papers, it was a local supersymmetry, so supergravity, and there one can do the same, and the story is actually long for fermionic part of it, but for boson, not only long, but we're still working it. But for bosons, everything is very, very simple. It's much simpler than it was before. So the rule is the following. You take the previous theories, which everybody knows how to deal with. You calculate all expressions for potentials, for whatever. And then you say that the scale field S, which you want to call nilpotent field, is square is equal to 0. There is no bosonic part of it. You say that it is equal to 0. That's all. Okay. So this is a very simple procedure, and doing this you can achieve quite a lot. So one may say, okay, we do not know whether it's interesting or not, but apparently, and this was this recent paper, there is a relation between this theory and also the theory of D-branes. And also what is possible, we were able to formulate lots of different models. Right now, we can take all previous models which did not work and some which did work, and now try to reformulate it in this way. And many models which did not work suddenly start working because we do not need to care about this scale field S. So in particular, you take the simplest Keller potential, you add this linear part and constant part, and you can adjust the value of the cosmological constant, and you can also have supersymmetry breaking at any value you want, determined by these parameters. And what is good about it, usually when you want to break supersymmetry, there's a standard trick. You add something which is called Poloni fields. So after adding Poloni fields, this is an extra field. Here we do not add an extra field. But if you add Poloni fields, typically it's light. It has mass of the order of gravitino mass. Here, all masses of all fields are super heavy, so there is no Poloni problem, which was bothering cosmologists repeatedly for the last 30 years. So this is, well, pretty interesting. Then it is possible to go this way, and well, actually, even before you go that way, it was possible, that is a separate line of development, to try to find de Sitter vacua in the landscape. So we know that there is these different models like KKLT model, some other models, which are trying to, well, find de Sitter vacua in the landscape to achieve this 10 to the minus 120 to make some uplifting. But it was difficult, and when people try to formulate everything in terms of, well, supergravity or in some other way, usually in all approximations which people worked, there was no using of the fact that the supersymmetry is spontaneously broken in supergravity. When the supersymmetry is directly broken, there was very little control of the appearance of tachyons there. So there are lots of negative papers saying that it's impossible to do this, it's impossible to do that, in part because the supersymmetry was left apart. And here in this work, there was a method developed which can construct vacua is, with spontaneously broken supersymmetry, which by construction are stable, so there are no tachyons there. And there are many, many vacua like that. So this is a new development which is strange because people are trying to do it, and it was really extremely hard. And also, if you use nilpotent fields, then it becomes, well, nearly trivial. So you, for example, take superpotential of KKLT model, you add this field S, you uplift it, and then you say this field S is equal to 0, and your uplifting is still there. So that's, well, very simple trick to play. And then we have lots of different models in supergravity and supergravity related to string theory. As I said, I do not talk here about exactly string theory issue. But what I'm trying to say is that playing with these fields, you can easily construct pretty simple model where adjusting two parameters, you can cover all the plane for NS and R. You can have natural inflation in supergravity. Natural inflation was suggested 25 years ago. Until last year, there was was no supersymmetric version of natural inflation. So right now we have written a paper with 5 different realizations, supersymmetric realizations of natural inflation. So when we have this abundance of supergravity models of inflation, do we have any target, or we just do not have any predictions at all because we can predict now everything? Well, so here is an interesting and new other part of the story. In a certain class of models, which are actually pretty generic and interesting, models with non-minimal coupling to gravity, or some other models which we call conformal attractors, if in certain limits, independently of the starting point, you always predict the same, and that's the same these are values of NS and R. So in a very broad class of theories, we have definite predictions. These definite predictions, interestingly, are the same predictions as the one made by Starobinsky model and Higgs inflation model a long time ago, but now we see that these predictions are not just well confined to these 2 models. There are a very broad class of models with the same predictions. But if we study this a little bit more carefully, we will find that actually there are quite often 2 different attractors point. One is this and another for m squared, phi squared inflation. So whatever nature brings us, we have 2 possibilities to look at here, and which one is better, and we have lots of other possibilities in between. Now I am coming to the, well, concluding part of the talk. So we are waiting right now, and this is going to happen 2 weeks from now. So we're waiting for the new Planck data release. And hopefully, this will also include the joint paper with BICEP 2. So many, many things which everybody were watching during the last half a year, hopefully will be at least clarified because these 2 groups of people are working together. All models described above are large field models, and nevertheless, they describe this R in the range of 0.1 to 0.001. So the goal is, if we study experimentally gravitational waves in this range, we're actually going to test all large field inflation models, and this may require quite a lot of time, but testing using gravitational wave small field inflation models is difficult. Now, this is just to give you the idea of the scale. If gravity waves are discovered, then the typical particles fly produced during inflation, fly with this energy, and this energy is this number in GeV, and this is square root of R. Dependence on R is only square root. So whatever we will find here, either it is 0.1 or it is 2 orders of magnitude smaller than that, we are in the range which is 9 to 10 orders of magnitude higher than LHC. So what Forbes magazine would tell about that, and that is a real citation, except for here they have written something like $12.5 billion, and I'm not quite sure that this is precise. Okay, the total cost of 10 billion, which seems like a bargain. I said, seems like a bargain, especially when you consider the fact, bringing them much closer than these mysteries of the universe. Oh, that's why they built this accelerator, okay? So now, the total cost of the Planck satellite, which arguably brings us much closer to understanding of the mysteries of the universe, which was an excuse for 10 billion, now it's about 1 billion. And the total cost of the BICEP experiment is about 10 million. So this means, first of all, that we just started how these people in Congress, they are, well, saying something like that. We have ways, we have means, but we do not have a consensus. So we have here ways. As about means, it depends on who is going to give this extra $10 million to these people. But we are way below everything else here. And this is the list of some of the gravity waves experiments which are under planning. I think that the next speaker will tell you more about the experimental status of the situation. Thank you.
Thanks, Andrei. Questions?
Scared.
Okay. Yeah.
So at the very end, you were saying you wanted to be able to, I mean, your theory seems to be able to predict any range of things that BICEP 2 might predict. And so you do get a generic prediction of the scale of the Hubble constant at error and the scale of the energy involved. But how are we going to disentangle the theory given something like a BICEP 2 measurement where we get R and NS?
Okay, so first of all, not every theory can explain everything that we see. And that's how right now 99% of all inflationary theories which have historically have been introduced, they are already ruled out. And then if you have additional data from BICEP2, from whatever other experiments, many other theories will be ruled out. Like, for example, if, well, people will find that R is, for example, 0.1, okay? Well, maybe 0.5, or even 100th, so 1%. All theories of small field inflation, and there are many of them, will be ruled out. There is a big table of theories based on string theory in a review article by Quevedo written a year ago. So there is a big table of all different models. Out of these models, essentially one model which Eva developed and one other model close to it, inflation. These two models, they predicting R in the observable range. All others predict R 10 to the minus 10. Okay? So then you say, all but one or maybe two models of string theory inflation are ruled out. This is a very, very strong result. So if we find something, it is going to be dramatic.
You wanna? Yeah.
That was a great talk. I just wanted to ask or comment one thing, which is the idea that one can continuously vary R and NS. It may be kind of the conservative view from a certain point of view, but when it comes to large field inflation, as we all know, it's sensitive to quantum gravity, and therefore, to be complete, we need to do it in that framework. And so far, we have a handful of possibilities for R and NS, and it might end up being that it's a more discrete set of possibilities. Sure. We really don't know. It could end up being more like a discrete Joum of almost continuous, but that remains to be seen. And so I just wondered, since you commented on a possibility of a continuous distribution, is that really what you mean, or?
Well, what I know is that several years ago, we did not have any good models of inflation based on supergravity. Right now, I have many, which, however, well, we did not study radiative corrections on them. If they're based on string theory, maybe there will be some, well, discontinuity between different predictions. However, if you are talking about string theory landscape, well, probably you'll find a model for every prediction you want.
Hey, Andrei. Andrei, how many of these models have low-energy superpartners that might be accessible at the LHC?
Well, that was the part which I tried to describe. So if you want how many of them, because we have right now, it's analytical, the set of functions you can change continuously, there could be many. But if you try without thinking much, you quite often, typically, get huge gravitational mass. So many of the things which we were trying to do, we were trying to construct models which can produce you small gravitational mass, which may be a wrong idea, because we did not see low energy superpartners. But these are the tricks with all of these nilpotent fields in particular. You can actually, I've shown you the simplest model, but you can add other nilpotent fields which will not make your calculation for inflation more complicated, but each of them will be solving its own problem. One will be responsible for, the height of the potential, another for supersymmetry breaking, and then you can fine-tune it to any number. In the classical approximation.
Yeah, one has. So just wait.
The microphone so that we can record. Thank you.
Yeah, so am I correct in thinking that you can start with any bosonic model, and then you add a fermion with suitable couplings, and then it will become this spontaneously broken supergravity model?
We are not, once again, I do not understand. I am not adding any fermions. What we are doing right now, we're studying bosonic sector of the theory. Actually, fermionic sector of the theory, which I mentioned, if we add these nilpotent fields, it becomes much more complicated.
Yes,
it is still in works.
Yeah, I had a similar question, but it's nothing. Yeah.
Thank you.
Yeah, I'd like to follow on Juan's question. My interpretation is that the answer to Juan's question is yes. Namely, every bosonic model that you take, you add this field that squares to 0, and it becomes supersymmetric. Yeah. So in that sense, I don't see what, and since you're not discussing the fermions anyway, you might as well say that the class of models you study is any model without supersymmetry.
This is an optimistic point of view, but because it is not done yet, we do not know for sure. Who knows? Maybe there are some hidden things. Like when we studied Higgs inflation, people came with, "Oh yeah, you have this unitarity bound." I do not think that this was the right thing to say, because I don't think that there is a unitarity bound. But this is some unexpected things. Here, once we do not describe fermions yet, there could be some tricks on the way. I do not see these tricks. This is a specific thing where some information is eaten by gravitinos, some at least Goldstino things, they're eaten by gravitinos potentially. So maybe there is no problem, and then we are at optimistic camp. As of now, when we study inflation, this is just a God's gift to have this opportunity of making much simpler model where you do not really need to study lots of fields moving and not having Poloni field problem.
Okay, I think we should move on. Thank you for Andrei again.